Hello students. So the next part from this chapter is atomic models. So after the discoveries of all these subatomic particles like electrons, protons and neutrons, what is the next challenge for the scientists? The next challenge is how these particles are arranged inside the atom. Yes or no? So based on that we have different atomic models were there. So everything we'll discuss. First one is called as Thomson's model of atoms. So in the same Thomson who discovered electrons gave his own model of atom, that is called as Thomson's model of atom. So students, according to J.J. Thomson, this is how the atom looked like. So the whole atom, and one more thing, during this model of atom, neutrons were not discovered. Neutrons discovery is a very recent discovery in the year 1932 or 1935, around that time. So we have only the discussion about protons and electrons only. So let's see the model of atom according to J.J. Thomson. So this is how the atom looked like, students. The whole atom is covered by positive charge according to J.J. Thomson. You can see the orange part. The whole orange part is like protons, and inside this orange part electrons were randomly arranged, embedded in between this positive charged part of the atom. So this is how the atom looked like according to J.J. Thomson. This atom is compared to the watermelon also. If you cut the watermelon, you can see inside the watermelon, the red color part is there, seeds are there, yes or no? The red color part is like protons and the seeds are like electrons. That's why this model of atom is also called as watermelon model, or also called as plum pudding model of atom also. Plum pudding means it's a cake, fruit cake, yes or no? The cake part is like protons and the fruits are like electrons. Ultimately, according to the Thomson, the whole atom is covered with protons and electrons occupy very small spaces here and there. That is Thomson's model of atom. Answer: is this model of atom is correct or incorrect? This model of atom is completely invalid. Why? Because he didn't explain any stabilities, but he explained neutrality of the atom. What he said? He said the number of positive particles inside an atom are equal to the number of negative particles. That means the number of positive charges are equal to the number of negative charges. Then only atom is electrically neutral. That point he gave, but he didn't explain any stabilities. And one more thing, this model of atom doesn't have any experimental evidence also. It is simply an assumption of J.J. Thomson. Very simple. Got the clarity, student? Thomson's model of atom. Next model of atom is given by Rutherford. You can see, look at the setup, whole experimental setup. This atom, this model of atom has an experimental proof, and this experiment is called as alpha ray scattering experiment, students. Alpha ray scattering experiment. The main objective of this experiment is Rutherford want to prove, he want to give a proof to the Thomson's model of atom. He want to prove it, whether it's wrong or right, or he just want to prove the Thomson's model of atom. For that, we have a radioactive source like polonium or radium, and we have some lead slits. From this, alpha rays are passing through. What are these rays are called, students? Alpha rays. What is alpha ray? Alpha ray is a helium nucleus, He+2. It contains 2 protons and 2 neutrons. What is alpha ray? It's a helium nucleus. It contains 2 protons and 2 neutrons. This is called as alpha ray, the simplest radiation coming from the radioactive element, students. What is the charge on this alpha ray? 2 protons, 2 neutrons. Neutrons are no charge. 2 protons are positive charge. What is the overall charge on this alpha ray? Positive charge. Yes or no? What is the charge? Positive charge. I will explain the objective of the Rutherford's model of atom. He took a sample of gold. Okay, gold contains gold atoms, right? And he want to shoot this alpha rays towards a gold foil. Alpha ray is very small particle. Gold atomic number is 17, and it's a big atom, yes, comparatively to the alpha ray. And how he want to prove Thomson's model of atom? You know, students, what is the model of atom according to J.J. Thomson? The whole atom is covered with positive charge, right? He selected a positive ray, right? And he is shooting this positive ray towards a gold atom. If Thomson is correct, if J.J. Thomson is correct, what will happen to this positive ray? It will repel back. Sir, why? Positive, repel with each other, yes or no? Thomson said the whole atom is occupied by protons and alpha rays have positive charge. Positive, they repel back. If they repel back, Thomson is correct. What if they pass through the atom? Thomson is incorrect. Simple logic, yes or no? If these particles, if they pass through atom, Thomson is incorrect. Got the clarity? That's what the objective behind the experiment. For that, he selected radioactive source. So from there we are getting alpha rays, and lead slit is taken here. It contains a small hole. Why? Because, students, the alpha rays which are coming from this radioactive source are in irregular directions. We want a single unidirectional. Yes or no? So for that, lead is one of the densest metals. So lead is taken, and here gold foil. This is all, students. This is gold foil is taken here. Why? Because gold, instead of gold, if you take a beryllium, what will happen? We discussed in the previous video, discovery of neutrons. When helium alpha rays are shooted towards beryllium, we'll get carbon. Yes or no? Discovery of neutrons. They can be reactive nuclearly. Understood? But gold is a stable element. How gold exists in the nature as gold directly? It is a least reactive element. That's why gold is taken. Not only least reactivity, gold is highly malleable also. That means we can make a very thin sheet of gold foil also, which is the best suitable for the experiment. So that's why gold is taken. And surrounding the gold, we have phosphorescence material is coated, students. You already know the reason for phosphorescence. Yes or no? To observe the deflections, to observe where the alpha rays are striking back, how they are reflecting back, whether they are passing through or not. To observe everything, the surrounding material is phosphorescence. Now, once these alpha rays strikes to the gold foil, what are the observations? Already there on the screen. You can see majority of the alpha rays, students, majority of the alpha rays, they passed through the gold foil. What does it mean? You simply answer. You decide Thomson's model of atom is correct or incorrect. Absolutely incorrect. Proven wrong. Yes or no? If Thomson is correct, they should deflect back, right? But majority of them pass through the gold foil without any deflection. That proves Thomson's model of atom is incorrect. Some rays are deflected by small angles, you can see. And very few rays deflected completely in the opposite direction. That means the alpha ray which striking head-on collision with the proton is coming back. So that all the clarities we'll discuss in the coming slide. So this is alpha ray scattering experiment. 3 observations. Majority rays pass through the atom. Thomson model is wrong. Few rays deflected by small angles. One ray out of 12,000 or 20,000, one ray is completely deflecting backward direction. So what does it mean? That we'll discuss in the coming slide. Students, Rutherford observations. Look at here. Since majority of the rays pass through the gold foil without any deflection, Rutherford said the whole majority of the atom is occupied by empty space. No, nothing is there. What Thomson said? Majority of the space is occupied by protons. But what Rutherford proved? Majority of the space is empty space only, nothing is there. And few rays are deflecting to the small angles. You can see, yes or no? Which rays are deflecting? The rays which are coming near to the nucleus, they are deflecting. And which rays are coming back? The rays which are directly hitting to the nucleus, hitting to the proton, they are coming back. And these rays, the percentage of these rays which are coming back, are there more or less? Very less. What does it mean? The protons occupy more space inside the atom or less space? Less space only. If more space, more particles will reflect back. Yes or no? Is it happening? No. Very less particles are coming back. What does it mean? These protons occupy very small space. And this is called as nucleus by the scientist Rutherford. This is called as nucleus. And what the nucleus contains? Nucleus is made up of protons and neutrons. Ultimately, neutrons are no charge. Protons are there, na? So what is the charge on nucleus? Positive charge only. So that's how the discovery of nucleus was done by this experiment, students. That's why this model of atom is also called as nuclear model of atom also. Next, arrangement of electrons. So, and in addition to the nucleus and protons and neutrons concept, Rutherford, while giving his model of atom, he explained about electrons also. He said electrons are revolving around the nucleus, like how the planet Earth is revolving around the sun. Electrons are revolving around the nucleus. That's why this model of atom is also called as planetary model of atom or solar model of atom. Ultimately, this is the model of atom according to Rutherford. This model of atom correct or incorrect? That we'll discuss in the coming slide. Nucleus is completely correct, right? But what about electrons? Alpha ray scattering experiment is anything to do with electrons? No. But why he gave? Students, Rutherford is giving a model of atom. Can he give a model of atom with only protons? I know where the protons are there, so I explain only protons. No. Atom means definitely he should mention protons, electrons and neutrons. At that time, neutrons were not discovered anyway. So that's why he added the electron point also. But there are some defects because of this electron point. Listen. As per the laws of electrodynamics, Any charged particles moving at high speed in a circular path will radiate energy continuously, and the electron, when it moves around the nucleus, should lose energy and get increasingly pulled towards the nucleus with greater force. So what the defect is, students, when any charged particles, if it is moving in a particular motion around the nucleus, it loses some energy. If it loses energy, this is the nucleus. This is the nucleus. If this electron is losing energy, what will happen slowly? It comes closer to the nucleus, it will collide into the nucleus. Is it happening? Are the atoms are colliding? Are we exploding? No, right? Understood? This he didn't explain. Why electrons are not losing energy? What are the forces acting on them? Nothing, he said. So he said some points about centrifugal force and electrostatic force of attraction, but he didn't explain about any stabilities and factors about electrons also. Rutherford could not explain the stability of an atom. He could not explain the distribution of electrons around the nucleus. So like in different positions, right, students, electrons are there. He didn't said anything. In first position how many, second position how many, third position, he didn't said anything about distribution of electrons around the nucleus also. But whatever he gave about protons and neutrons is absolutely correct. So next, Bohr's model of atom. So of course, obviously, proton, neutron we already know by the Rutherford. Electrons he just gave an arrow. He just gave guess. That is not proven. So next, definitely we need to focus, the scientists need to focus on electrons. Yes or no? This about electrons. The next model of atom is given by Niels Bohr model of atom. Niels Bohr conducted experiments on hydrogen, students, on hydrogen, and he explained how these electrons are revolving in the around the nucleus in the hydrogen atom. So look at here, electrons revolve around the nucleus with fixed energy in concentric circular paths called as orbits or shells. These are called very main point, friends. They are called as orbits or shells. These orbits are denoted as 1, 2, 3, 4 or KLMN. I will draw the model of atom. See, this is how it looks like. This is the nucleus. 1, 2, 3, 4. Electrons are revolving around the nucleus in circular path. Each path is called as orbit or shell, and he named these shells as K, L, M, N. And what are the numbers? 1, 2, 3, 4. Okay, these are the numbers. Next, the electrons have the least energy in the K shell and the highest energy in the N shell. And obviously, from K shell to the KLMN, energy is increasing. That means which shell has least energy? K. Which shell has highest energy? N shell. Understood? So in shell wise, what is the shell path? There is a path. In that path, electrons are revolving. Sir, only 4 shells are there, more than that? That we have the coming academic year discussion, students, whether more shells are there, limited only 4 shells are there, everything we have the discussion, but not now. As long as the electron revolve in a same circular orbit, energy is neither radiated nor absorbed. That means the point is, if electron is revolving here, it neither loses energy nor gains energy. It is simply revolving in that position only. Why? Because its energy is fixed. That is called as quantized. Its energy is fixed. Because of this fixed energy, it neither loses nor gains energy. It's simply revolving in that position only. But if you provide external source of energy, sir, how can we provide external source of energy? By heating, by electricity, by sunlight. Yes or no? These electrons gains energy. They can jump to the higher energy levels also, students. These electrons, they excites to the higher level. If more energy, they will be knocked out. Understood? When electrons are exciting, jumping from lower to the higher level, while you provide energy, if energy is not sufficient at that stage, electrons are highly unstable. Again, they fall back to their normal position by releasing one radiation. This radiation is called as electromagnetic radiation. Electromagnetic radiation, the radiations which are coming from the sun, visible light, UV light, microwaves, cosmic rays, infrared, all are radio waves, all are in electromagnetic radiations only. They contains oscillating fields of electric field and magnetic fields, EMR. Okay, how these radiations are produced? Because electrons gains energy, excites to the higher level. Again, they release energy, falling back to the normal position. And this energy is EMR, electromagnetic radiation. So, energy of an electron changes only when it moves from one orbit to the another orbit. When electron jumps from an inner orbit to an outer orbit, energy is absorbed and it falls back, energy is released. This energy is released in the case of EMR, electromagnetic radiation. Then what are the defects? Is this model of atom correct? Look at here. Bohr's theory is applicable for single electron atoms only. What is the atom with single electron? Hydrogen. Yes or no? So this model of atom is applicable only for hydrogen-like species. Look at here, He plus 2. It contains how many electrons? Sorry, not He plus 2. He plus 1 electron. Li plus 2, 1 electron. Be plus 3, 1 electron. Why? Because students, if more electrons are there, electrons are not only revolving in circular shapes, they are revolving in different shapes, which is not explained. Why? Because he conducted experiment on hydrogen atom. Understood? That's why this model is applicable only for hydrogen or hydrogen-like species. What's the meaning of hydrogen-like? The particles which contains 1 electron, right? Bohr's theory could not explain the structure of atoms of higher elements such as helium, lithium, beryllium. So for higher elements, he didn't explain. Only for hydrogen, he explained. Bohr's theory could not explain the formation of chemical bonds by the atoms. Yes, sir, he's explaining about electrons. Electrons are the reason for the chemical reactivity. He didn't explain anything about chemical reactivity. Why they form this bond, why they form that bond, why it is combining with that element, this element, nothing. He simply explained orbit concept, that's it. Next, Bohr-Bury scheme. So this explains about, students, in every shell how many electrons maximum any shell can accommodate, any orbit can accommodate, which is given by a simple formula. The formula is called as 2n square. N represent the shell. Okay, and represent the shell. First shell, 2 into 1 square. How many electrons first shell can accommodate? 2 electrons. Second shell, 2 into 2 square, 8 electrons. Third shell, 2 into 3 square, 18 electrons. Fourth shell, 32 electrons, and so on. This is Bohr-Bury scheme, explains about the distribution of electrons in different shells. Mainly, clearly, this was explained after in quantum mechanics, students. Quantum numbers will get in the higher classes. Why only 2 electrons? Why only 8 electrons? Why 18? Why? Because these electrons are not revolving in spherical shape. Different shapes are also there. That will be discussed in the subshell concept, quantum numbers concept in the coming academic years. And this academic year, you have to remember this. And according to Bohr-Bury scheme also, they said an electron, an atom becomes stable if this shell is completely filled. Maximum it can completely filled means 8 electrons. If it contains 8 electrons, that gives the stability. Once if it fills the 8 electrons, then it can enter into the next shell. So this is Bohr-Bury scheme. The formula to be remembered in this is 2n square. N represent the shell number. KLMN or 1, 2, 3, 4. These are called as shells or orbits or energy levels. All indicate the same. Next, valence electrons. Valence electrons means simply, first of all, students, this is an atom. This is an atom. Electrons are revolving in different shells. Yes or no? The last shell, what is the last shell? This one. This is called as valency shell. And the electrons present in the valency shell are called as valence electrons. Understood? The electrons present in the outermost shell are called as valence electrons. That's it. And what is valency? The combining capacity of an element is called as valency, students. The element, any atom, participate in the chemical reaction in order to achieve 8 electrons in its valence shell. To achieve that 8 electrons, this atom can definitely participate with 1 electron or 2 electron or 3 electrons. Yes or no? That becomes the valency of that element. So the combining capacity of an element. The meaning of combining capacity means you already know how chemical reactions takes place. Chemical reactions mainly takes place by 3 ways: losing electrons, gaining electrons, sharing electrons. How many electrons an atom loses? How many electrons an atom gains? How many electrons an atom shares? That is valency. What are valence electrons? The total electrons present in the last shell, valence electrons. What is valency? The electrons which are participating in the bonding. How? By losing, by gaining, by sharing. That is valency. So next, ions. Ions are the charged particles, right? How do ions form? When an atom loses electrons or gains electrons, they form ions. Mostly we have cations and anions, students. Cations are the positively charged particles, anions are the negatively charged particles. When do cations form? When an atom loses electron. When an atom loses electron, it forms cation. When an atom gains electrons, it forms anions. Ultimately, these ions are coming from atoms only. Yes or no? So, what are cations? Positively charged particles are called as cations. Look at here. First example. What is the example? Sodium ion. What is the charge? Na plus 1. That means sodium atom, when it forms Na plus, if it lost 1 electron, Na plus 1. Magnesium ion, Mg plus 2. When it forms Mg plus 2, when it lost 2 electrons. Aluminium ion, Al plus 3. When it forms Al plus 3, when it lost 3 electrons. Chloride ion, when it forms chloride, when it gains 1. Oxide, when it gains 2. Fluoride, you say F minus, when it gains 1. Nitride, when it gains n minus 3 means when it gains 3 electrons. The points to be remember is cations form when an atom loses electrons. Sir, why do they get the positive charge? Why? Because if electrons were lost, now the number of protons are more than electrons or not? The number of positive charge dominates or not? That's why they get a positive charge, right? Sir, why anions get a negative charge? Electrons are gained, negative particles are gaining. Now which particles are more? Negative particles are more. So the net charge is negative. Sir, why minus 3? It gains 3. That's why more 3 negative particles are there. Understood? Got the clarity, students? So this is a discussion about ions also. Next, we have some terms and definitions to remember in this concept of structure of atom. First of all, atomic number indicated by Z. Simply atomic number indicates number of protons present in an atom is called as atomic number. What is atomic number? Number of protons present in an atom. We can also define atomic number in terms of electrons also. Number of electrons present in a neutral atom. Why? Because neutral atom contains same number of protons and same number of electrons. What is atomic number? Number of protons. What is in terms of electrons? Number of electrons in a neutral atom. For example, aluminium. Aluminium, students. Atomic number. Aluminium contains 13 protons. What is its atomic number? 13. So where to represent the atomic number? Subscript position down on the left side or right side. Yes or no? Carbon. Say how many protons are there? 6 protons. What is the atomic number? 6. Oxygen. 8. Say what is the atomic number? 8. Why? It contains 8 protons. Understood? So that is atomic number. Always indicate at what position? Subscript position. Left side or right side. Mass number. Mass number is indicated by A. Sum of protons and neutrons is called as mass number, students. For example, carbon atomic number 6, mass number is 12. Mass number is 12. Protons plus neutron count is mass number. And where to indicate mass number? Always at superscript position, top position, right? And this number indicates protons plus neutron. This number indicates proton. Students, how to find the number of neutrons? This number minus this number. Yes or no? This number, mass number minus atomic number. What we get? Proton will be cancelled out. We'll get number of neutrons. So this is the formula to remember. Number of neutrons equal to mass number minus atomic number. For example, oxygen atomic number 8. Its mass number is 16. So how many neutrons are there? 8 neutrons. How many protons? 8 protons. 8 plus 8, 16. How many electrons? 8 electrons. Neutral atom na? Protons are equal to electrons. So this is about mass number, students. Next we have isotopes. About isotopes in the previous video we already discussed in the Dalton's atomic theory. Yes or no? Isotopes means atoms of same element with same atomic number but have different mass number. Why the mass number is different but atomic number is same? That means number of protons are same but the mass number is getting different. Look at here, protium, deuterium and tritium, and look at the atomic number. Protium 1, deuterium 1, tritium 1. Sir, what are all these protium, deuterium, tritium? They are all hydrogen atoms only. Why? Because their atomic numbers are 1, 1, 1. Protons are 1, 1, 1. Then where is the difference coming from? Number of neutrons. In protium, 0 neutrons, no neutrons. In deuterium, there is 1 neutron. And tritium, 2 neutrons are there. That definitely there is a change in mass number or not? Look at the mass numbers. Protium 1H1, deuterium 1H2, tritium 1H3. Are these the different elements? Same elements. Then what do they have? Different mass numbers. So they have different masses. They are called as isotopes. Same elements, different masses. Why, sir? Why different number of neutrons? That's why. Next. So all these elements, while finding the mass, definitely we need to consider isotopes of different elements. Yes or no? For example, hydrogen means there is only one proton. Can we say write 1 gram? No. We have to consider deuterium and tritium also. So we have a formula to find the relative atomic mass. Students, the formula is mass number of first isotope into its abundance plus the mass number of the second isotope and its abundance by the total abundance. That's it. That means, students, for example, chlorine 35, mass number is 35, its abundance is 75%, and chlorine 37 is 25%. This is the formula. 35 its mass number into its percentage of abundance plus 37 one more isotope into its percentage of abundance by total 100% equal to, what's the mass we got? Chlorine 35.5. 75% is chlorine 35 only. Can we say only 35? No. You have to include all the isotopic mass and you have to take the average relative mass. This is called as relative atomic mass, 35.5 grams. So that's why that's the reason why we have atomic masses in decimals for the elements. We are taking the average of all these isotopes into its percentage of abundance also. So next we have isobars. Isobars means, students, different elements but with same masses. That means atoms with different atomic numbers but same mass numbers. For example, examples are given here. Argon, its atomic number is how much? 18. Mass number is 40. Next, calcium, potassium is also there. Atomic number 19. Mass number, isotope of potassium is there. Next, calcium 20, 40. These three elements are the same or different? These three elements are different. Atomic numbers are different, right? Protons are different. Proton is the main subatomic particles which gives the difference, students. But look at all, they have same mass numbers or not? They are called as isobars. So what if they have same mass number? Do they have any same property? Nothing. They don't have any similarity. But they have one similarity. What is that? They have same mass. They have same mass, right? Next, last, isotones, students. Isotones means atoms with different atomic number, different mass number, but they have equal neutrons. They are called as isotones. For example, 1H3 tritium, helium. Atomic number different, mass number different. Find the neutrons. 3 minus 1, 2 neutrons are there. Find the neutrons. 4 minus 2, 2 neutrons are there. They contain equal neutrons or not? They are called as isotones. That's it, simple. Look at the example. Silicon, phosphorus, sulfur are given. Atomic numbers are 14, 15, 16. Mass numbers are 30, 31, 32. But look at the mass number, atomic number difference. 16, 16, 16. They have same number of neutrons or not? So these particles with same number of neutrons are called as isotones. So these terms and definitions are very, very important. Atomic number, mass number, isotopes, isobars and isotones. So this chapter is completed, students, about atomic models and these terms and definitions, everything we discussed. I hope you got an idea about this chapter and I hope you got the clarity. Thank you, students.